I mentioned in the second video that it could be useful to create a spreadsheet to crunch through the calculations for you. I have the one I developed here. For what I treat as my constants, I set up 4 values: the switching frequency, the catch diode voltage drop, the delta I ripple current percentage, and the output current. Since some of these constants can be reduced, I do that here with delta I and output current to create denom, the value of the denominator of the left half. I then created an array of input and output voltages, V in horizontally and V out vertically. Then, simply for convenience in validating that I had entered the formula correctly, I divided the formula into the left and right halves, here and here, followed by their product here. This follows the structure of the formula back on page 18 of the datasheet. Here's the left half, here's the right half, separated by the multiply operation. This last section is the important one, the product of the left and right halves. As I show highlighted in blue for output voltages of 2.5, 3.3, and 5 volts, I select the inductor value based on the last column at 20 volts input. Let's now use the Worth RedExpert online tool to validate the inductor. The tool is found here. we-online.com/RedExpert. We select buck for the topology, then enter the values. We'll use as an example the 5-volt handy supply and assume 3 amp continuous nominal output current. From testing, I know that the IC needs at least 2 volts of headroom to regulate, so our Vin min is 7 volts. We'll use 12 volts as Vin nominal and Vin max as 20 volts, the limit of the 2303 IC used in handy supply. Our nominal switch frequency is 700 kHz, and the catch diode forward voltage drop is 490 millivolts. You notice, just for interest's sake, that the simplified schematic here is essentially the same as that shown on the first page of the datasheet, with the understanding that the series top MOSFET is internal to the 2302-2303. As I mentioned in the first video, all buck designs are essentially identical, so this RedExpert tool, for example, can be used with any buck IC design, be it from analog, linear, microchip, TI, and so on. From other considerations I don't review here, performance, specs, price, availability, I've chosen the WE-PD series, so I select them from the drop-down list here. We see that the RedExpert tool has selected about 10 inductor candidates for us. If we sort by inductance, we get values of 3.5 to 6.1 microhenry. Going back to the spreadsheet, we can see that the inductors RedExpert selected correlate well with the input voltage values between about 9 volts up to about 18 volts. So it looks like we have an independent validation of the spreadsheet calculations, and this is a good thing. Let's select the 6.1 microhenry device and check the current temperature derating curves. As you can see, and which is true for all inductors, inductance drops as current rises. You'll also notice that we have a real-time XY cursor. Since the 2303 current limits above 3 amps, we easily stay in the flat part of the inductance versus current curve here. So far, this device is a good candidate relative to the needed inductance and current. Checking the temperature rise versus current curve next, the real-time cursor also shows that there is very little heat generated at a 3 amp load, only about 7 degrees Kelvin. So the 7447 7006 inductor would be a good conservative choice. By the way, you may have noticed the Display Details button here on the left. Once we click this and ensure all panels are open, we see a summary of the buck setup, the switch activity based on the nominal voltage in, and then estimated inductance values. Beyond these, you'll see the ripple current graph, the total ripple current delta, and the peak current. Last of all, we also see the losses graphs and estimated device temp increase. For handy supply, these are nearly unimportant because they are so low, and in fact, actual testing confirms the temp rise is very low. If we select another device, the information here on this pane changes. I'll select a few just to demonstrate. Clicking again on Edit allows us to change the specs. Before leaving this tool, let's manually change the inductor range. I change it from 5 to 8 microhenry to enable us to check the 6.8 microhenry inductor that I chose and listed on the spreadsheet. In this case, these inductors were chosen for price and availability during the design phase. We find the 744709006, a 6.8 microhenry inductor, right here. We confirm that both the derating curves have a very comfortable margin, so this device will function well in handy supply. And in fact, I've tested it and it works as expected. We need to handle one last item. If you've been following along carefully, you might be wondering about something on my spreadsheet. Let's look again at this final calculation for a 5-volt output. You might be asking, if you plan the inductor size for 20 volts input, what happens at a lower input voltage? The spreadsheet shows, for example, at 7 volts input, we need an inductor of only 2.32 microhenry. So what happens now? Well, the answer is part of the compromise I mentioned earlier. If we go back to the datasheet, page 17, and plug in the inductance value to solve for ripple current, we find that ripple current increases. And this makes sense, doesn't it? Treating the rest of the equation as a constant and varying only inductance, the simple rules of algebra clearly shows that as inductance decreases, ripple current must increase. They are inversely proportional. What you, the engineer, have to determine is whether the ripple current value is acceptable in your application. Again, this is what I mentioned in the handy supply intro video regarding why it isn't possible to build a power supply that can be adjusted from about 1 volt to 5 volts, even if the divider network could be constructed, and it certainly could be, because the ripple current would get out of hand for a fixed inductor size. Buck mode power supply design is no longer the exclusive realm of only the very experienced analog designer. They can be safely and reliably used by careful engineers willing to spend the time with the datasheets and follow the recommendations for PCB layout. You might have to spin a rev or two before you get it right, but in fact, today's devices are so highly integrated and sophisticated that using them is very straightforward. Carefully following the formulas will go a long way to keeping you out of trouble. I hope that you found these videos helpful and that they encourage you to experiment with new devices and designs, to try new things. Thanks for watching.